So we are on Electricity and Magnetism Part 2. If you are new to the stream or new to my channel on YouTube, you can find Part 1 as well as some other discussion series we've done, including path integration and what else do we do, guys? Lagrange mechanics. And we're running another course on Fridays when I can stream, which is quantum computing. Let's see what else is there. Oh, so the notes are on Discord. So if you're in chat, / Discord for the notes. Or if you are on YouTube, all of that stuff is down in the description below. Actually, variational methods in E&M would be pretty legitimate, interesting to see. Yeah, and there's, well, we're doing cheap variational method today. Like I said, Griffiths is very hand-wavy, and this is one of the hand-wavy things he does. I mean, like, I wouldn't have been able to do this when I was an undergraduate anyways, the variational method of this stuff. So I'll take his word for it. But, like, you could do variational method with the stuff we're doing today for sure. Okay, but we're just gonna cut corners on it. But yeah, so notes are on Discord. Anything else? I don't think I'm doing anything. Anyways, let's start Electricity and Magnetism Part 2. Let me hike up my britches. Oof. Ooh, that's right about where the edge is, huh? Wow, why am I so... Let's move over just a hair. There we go. I feel like we're kind of squelched on this side. Yeah, we are. Okay. All right, so we'll just have to be careful about that. Okay, so... Shirley, if you want to put your question in the queue, I will, Oh, it's blurry. I never focused it. Thank you. Shirley, if you want to put your question in queue, we can grab that at the end of stream. There you go. Okay. That should be better. Yes? Yeah, it looks better, huh? Okay. Let's start with last time. So last time. It's really weird how far over I am, but whatever. We're gonna go with it. So we derived the first Maxwell equation, right? We wanted to derive the Maxwell's equation. That's kind of the purpose of this E&M course. And we found that the divergence of the electric field is equal to rho over epsilon naught. So again, the notes are on Discord. You can just follow the Discord and ask away, or grab the notes off the Discord in the discussion series notes section of Discord. And then, yeah, follow along so you don't have to take your own if you'd like. And we derived this from Gauss's law, which is one of the most important formulas in all of E&M, which said the flux around a closed surface.
Why are you dividing by 1?
Dividing by 1? What are you talking about? I didn't divide by 1. Me? Where did I divide by 1? Here's epsilon naught. Oh. Natural, are you doing natural units? Tell me you were doing natural units. Please. That'd be really funny. Okay. I think everybody divides by 1. And everybody should do natural units, but we won't be doing natural units too much in this course. So then the flux through a closed surface is equal to the surface integral of E dot dA. It's very important that we talk about this as the area of the Gaussian surface. That was good. The area of the Gaussian surface, the surface area of the Gaussian surface. And then this is always going to be equal to the charges enclosed in the surface divided by epsilon sub naught. So this is what we're dealing with. This is Gauss's law. Very, very important. We derived the first of the Maxwell's equations from using Gauss's law. But where did we start? We started with talking about the Coulomb's force law, right? Maybe I should write Coulomb's. Coulomb's, so I can be cool. I want to be cool in the Coulomb's club. Coulomb's force law, which basically stated that we could have some force of, if we had a source particle and a test particle, or a source charge and a test charge, we could write some sort of interaction forces between them that were mainly done by observation, where we have this crazy R squared, which is the distance between the two. And if we had many of these forces, many of the source charges and one test charge, then we could write them as a superposition of all the forces or a superposition of the electric field. So I'll write the superposition form of the electric field, which is basically if we want, and you could write it as a single two particle, or a one particle electric field. But we did, and we saw that this, that this had, each charge had an intrinsic field associated with it, and that was called the electric field. And you could write it as a superposition adding up over all of the source charges. Crazy R I squared R hat. Like I said, we're basically the electric field is generated from each source charge, and then this crazy R is the distance between each one of these to some point. Like this one is the test charge, but you can talk about the electric field as a point. So what do we got here? Oh, Chili Snap, thank you for the follow. Welcome. You've had good questions. Okay, now, what else do we got here? Oh yeah, so now we are, so that's what we talked about last week. Both of those force and the electric field follow the law of superposition. We can basically see the big difference between the two of them is the force is equal to the source charge, or I'm sorry, the test charge multiplied by the electric field associated with all of the source charges. And that's that. We see an electric field in real life. We know it exists. We can see the effects of it. And because of that, we know that there's some field associated with the source charges. All right. Now, there is 3 symmetries associated with Gauss's law. I think this is very important.
Son of Anubis, I greet you with an open heart and a quantum physical happiness.
Hi, Tropical. Good to see you. Good to see you. It's always good to see you, Tropical. Okay, let's, now we have to go back and track. We're going to actually go to last week's notes where we had to stop for the sake of time because we were really going over. And let's talk about Gauss's law, a prescription method. So we really want Gauss's law to be something we know how to use. And I'm going to break it into 3 steps, okay? So these are the 3 steps. Every time we get a Gauss's law problem, we're going to use these 3 steps to solve it. Okay, so here it is. The first, step 1. So we want to find, and these are in the notes, general expression. How about a general expression? Find a general expression. Wow. Wow, wow, wow. Find a general expression for E field. In terms of Q enclosed. In terms of Q enclosed. Now there's a few more steps to this that are kind of in terms of Q enclosed that we're not going to like list out. Like you have to identify the symmetry first. We won't list that step out. That will be something that we do every single time. We'll just find a symmetry involved in each of the, in the situation, and then we'll take advantage of that symmetry using Gauss's law. That's kind of the point of Gauss's law, is to take advantage of the symmetry. So the first step really is to find a general expression for the E field in terms of Q enclosed, and we'll do that a few times. So basically the idea is to solve for the electric field. You're going to have this right here is going to be the main crux of the solution, and we're going to want this E to be isolated on the left-hand side with everything else on the right-hand side, including Q enclosed. And then we will end up going through each case-by-case basis. So that's the next step. So find Q enclosed for each radius under consideration. Yeah, so we'll go on a case-by-case basis where we're going to go by every time we get a radius away, we'll have to, change it up a little bit and find a new Q enclosed for that specific radius, okay? And then we'll just evaluate Gauss's law under that circumstance, right? Case by case. Okay, so, because Q enclosed is going to be the thing that changes as we move away from the center of, the object, whether it's spherical or cylindrical or or Pillbox, which brings us to the next step. What type of symmetries do we want to take advantage of? Like I said, Gauss's law is about symmetries. Griffith says there's only 3 symmetries to consider. So let's talk about those 3 symmetries. The 3 symmetries are, namely, spherical. So that's the first symmetry. Spherical. Cylindrical. And a pillbox. And we'll do more of these once we're done with the example. But right now, let's solve an example. Hey, guys, Milano. Okay. Good to see you. Good to see you. Let's do the 3 steps. I forgot to say the third step. Profit. Those are the 3 steps. Okay? Hey, Gaslit Heroes, good to see you too. 3 is a magic number. 3 is a magic number. What's pillbox? You'll see. We'll do an example soon with the pillbox. People call it a different thing. Griffiths just calls it a pillbox, and that's the one that my teacher called it too, because we use Griffiths. So let's solve the first example. So the first example that we're going to solve is find the field outside of a uniformly charged solid sphere of radius r and total charge q. So we'll have some solid uniformly charged sphere with radius r and a total charge of q. Okay? And now we're going to find the Gauss's law outside. So step one, find the general expression for the E field in terms of Q enclosed. So and part of this is finding the symmetry, and then there's the dot product. And I mean, like, we could go step by step. And when I do this in class, I really lay out a very large prescription. But then once you're in this level of E&M, the very strict prescription changes a little bit. So I'm just generalized it a little bit more for this subject. So we're going to start with our Gauss's law. The surface integral of E dot dA is equal to Q enclosed over epsilon naught. It's very important that you remember that this is always going to be the surface of the Gaussian. Remember flux. Flux is the measure of how much electric field is going through a surface, right? So now we have this charged sphere. There is an electric field
Step 4 is profit. Step 3 is magic.
This sphere is radiating an electric field, right, away from it. And then we can pretend that there's this imaginary closed surface around the sphere, and then find the flux through that pretend surface, that imaginary surface that we're making up. And that surface is always going to be our Gaussian. But we're not going to establish where that surface is right now. Right now, we just want to take advantage of the symmetries. So the symmetry of a sphere is obviously a sphere. So that's the symmetry we're going to be using. So we're going to want our Gaussian surface to be spherical. So when we say that this area is associated with the area of a sphere, it's going to be EA, right? Q enclosed over epsilon naught. And then remember, this dot product means there's a cosine theta, but we know that it's radially, that the electric field is propagating outward radially, which means if this is, the E field in every direction, and the surface is also some Gaussian sphere, and DA's direction is perpendicular to the surface, then E and A will be in the same direction. So that means this dot product is going to have a cosine of 0. And then cosine of 0 is 1. So we know that this dot product just boils down to E dA, and then this integral over the surface means we take consideration of the entire surface. So we're going to have some imaginary sphere. Let's draw it in a different color. Let's do orange. So we're going to have some imaginary Gauss's sphere around that, and we're going to be measuring the flux of the electric field through that. So this E is always going to be, or this A is always going to be a Gaussian surface. So the Gaussian surface is 4 pi r squared. And I use a little r because I'm not considering this big R. It's actually going to be the radius out to wherever we're interested in. I just did it on the outside, but we're actually going to be doing it to wherever. 1 gravity, 2 electric field, 3. So this is the Gaussian surface. R is the radius to the Gaussian surface. Right now it's just whatever we choose it to be. We'll go over it on a case-by-case basis. And over here we just have Q enclosed epsilon naught. Now we can then solve for E, and E is going to be Q enclosed over 4 pi epsilon naught R squared. That looks good, right? Now we can do, so step 1, check. Step 2 is to find Q enclosed radius for each radius under consideration. So we can do 2 of these if we want to. We can do, so that's step 1. We can consider step 2. And we can do 2 of these even though the problem only asks for 1. Let's start with the one the problem asks for. Finding a radius greater than R. So this would be if we found a Gaussian sphere outside of here. Then we just find Q enclosed. We're going to use, oh, well, we know Q enclosed is going to be the total charge, and the total charge is given to us. So it's just Q. So that's pretty straightforward, right? It happens to be very straightforward for this problem. The Q enclosed is just Q. And then so now we can just plug this stuff in, and E is going to equal Q over 4 pi epsilon naught R squared, which also happens to look very much like the electric field of a point charge, right? Which makes sense. If it's a uniformly charged sphere with total charge Q, then if we were to just go some distance away from it, it should just look like a point particle, right? We can model it like a point particle, and everything looks good. No, easy peasy, no problems. So now, now what do we do? Okay, so let's talk about the next case. So if this was case 1, we can consider a new case. Let's do it. I want to leave this up for just a second longer, so let's do it down here. This is case 2. And that is if R is less than or if little r is less than big R. So now we're considering a Gaussian surface that exists in, let's do a different color. How about, let's do green. So we can do a Gaussian surface that's inside here. We'll just do a solid one. And then with some little r that comes out to here, okay? Yes, Tyrion, I'm going to use little r twice. That's this business. You're in that business now, okay? Little r is the r associated with the Gaussian surface, and now the Gaussian surface is inside the big sphere. So now we have to find Q enclosed. This is not in Griffiths. This is just me explaining what we do in a different case, being more thorough. If we want to consider the density,
How dare you? Good day, sir.
there it is. If we want to consider the, hey Dodo, good to see you. We did, Ash. Hi, Lord Lycan. Okay, so we want to consider the volume density. Volume density is going to be the total charge. What do I have here? Oh, I did it wrong too in my notes. Nice. So the total charge, you're gonna have to follow the board and not the notes, and then we'll make the appropriate adjustments. It wasn't in the book, and now I'm looking at it thinking that's not right. So how do we solve this? The total charge density will tell us a couple things. We can do the total charge over the total volume. That's one thing that it's equal to. Another thing that it's equal to is the total, or the charge enclosed over the volume enclosed, right? Now, the density works to say it's a uniform density. So right now I'm going off from the notes a little bit because I realized I made a mistake. So you'll just have to follow along on the board. This is the volume enclosed, and basically what rho is telling us is this: no matter how much you enclose, how much charge you enclose, the volume enclosed and the ratio of the charge enclosed and the volume enclosed will always be rho. So if you consider the whole thing, it will be the total charge over the total volume. But if you want to close off a section of it, it's just going to be the charge enclosed over the volume enclosed. So this is what we're doing now. And we need to solve for Q enclosed. So Q enclosed is just going to equal Q times V enclosed over V. Blue Spider Monkey, thank you for the follow. Welcome to the channel. Okay, now, this is our new Q enclosed. And that's where the mistake is in the notes, so you can just adjust that accordingly. And this is the, so then if we were to write these down. We can write the volumes down, right? It's going to be Q times 4/3 pi little r cubed divided by 4/3 pi r cubed. So the 4/3 pi will go away, and we'll just end up getting a Q times little r cubed over big R cubed. Okay? So now this is our new Q enclosed. So we want to plug it into our formula. We can find out that the electric field, I'm going to go all over the place here, is just equal to Q enclosed, which is Q r cubed over r cubed, divided by 4 pi epsilon naught r squared. So we have 1 over 4 pi epsilon naught r squared times Q little r cubed over big R cubed. And then we can cancel away. These r squareds are going to cancel with 2 of these r's. And our final E field is going to be Q divided by 4 pi epsilon naught QR, over big R cubed. And that looks good to me. So that's going to be the answer to that problem for the case number 2. So now, so here we are. We have found the 2 steps. We have found the general expression for Q enclosed. That's relatively straightforward. And as long as you're good about this Gaussian surface. And then the next step is find case 1, which is little r greater than r, which is outside for our purposes. This was case 1. And then we just find Q enclosed, which happened to be total Q. And then E is equal to Q over 4 pi epsilon naught r squared. The second case was when r is inside of the sphere. That's a little bit more complicated because we need to invoke what the density means. So then this density, we can talk about Q enclosed is Q times V enclosed over V, and then we can write out what those volumes are, simplify that, and then plug it in for Q enclosed. And what do we get? Profit. And that was the example of the sphere. Now, let's go back up to today's lesson, or more of today's lesson, I guess. We didn't get to that last week, so. Let's erase all of this, and then we'll do another example with a pillbox. We're going to skip the cylindrical example, but I don't mind going over it afterwards in the question and answer time if you guys would like to.
How are we getting profit again?
Knowledge is profit. Is that, did I do good? Are you happy? Nice. Okay. I've lost my chalk. Okay, there it is. Now, we have 3 symmetries, spherical, and that's when and when we have a spherical object, we want to choose a spherical surface, a spherical Gaussian surface. So our Gaussian will be a sphere. Right now, the next one's cylindrical, and our Gaussian will be, can you guess it? A cylinder. And what's the Gaussian cylinder used for? Usually a line. So we'll say that too, because it's useful for a line, it's useful for a cylinder, it's useful for either of those 2 things. And basically, like, what we're trying to do is come up with an idea for where does this come into play, right? What type of object is going to require this type of symmetry? So a Gaussian cylinder would be good for a cylinder, obviously, but it'd also be good for a line, right? Because you can wrap it around. And then more specifically, something magical happens, which we'll talk about with our next example. But we do also have a pillbox, which is a Gaussian pillbox is for planes. Not like the plane, but instead the surface plane, like an infinite surface plane. Okay? So that's the example we're going to do, because I think there's some good quality in that example. And like I said, if you would like to see the cylindrical one, we can do it in the question and answer time afterwards. Okay, now let's do the next example. So in the notes, I have the question written out. I'll just read it here, and then we'll do what we do and solve it. A cylinder is just a thick line. There, there it is. Yes, it's very thick. like a bowl of oatmeal. Okay, so if we have an infinite plane, it carries a uniform surface charge density sigma, which just sounds weird to me anyways, but whatever. So it carries a uniform surface charge density. Bye, Admiral. Thanks for stopping by. Always good to see you. So we have a uniform surface charge density sigma on an infinite plane. Its E field, we have to find its E field. So find the E field of that thing. So if it's a plane, we want to use a pillbox, right? Okay, let's see here. So step 1, from our 3 steps, we have to find a general, I wrote step. Step 1, we have to find a general formula for the E field in terms of Q enclosed. So let's write our Gauss's law. The surface integral of E dot dA is equal to Q enclosed over epsilon naught. And now again, solve for EA. But let's just draw a picture to kind of grasp what's going on here. So if this is our plane, we'll have a little small pillbox. Let me draw this. Ooh, it hurts. There you go. So it has a little pillbox with a surface A. Okay, so it has a surface area of A. Now imagine there's one above and one below, so we can imagine having a pillbox here with a surface above and a surface below. And this has, some propagating E field like this that's normal to the surface. So the E field is normal to the surface, and it has, one on either side. So imagine that the pillbox exists on both sides.
Are we going to do the field tensor at some point?
Yeah, I think so. Later we'll do the field. Yes, the field strength tensor, like Griffiths does. But I'll wait for Griffiths to do it. So we can imagine adding up all of the different sides of the pillbox, right? Think about, it's just a box, right? So you just have this little box that exists, and there's the plane that runs directly through it, right? And it has 2 tops. And then it has 4 sides, right? Now, if we think about the plane being level here, so if this is the plane, and our box exists like this, where it's half above and half below, then we can think about the way that the electric field has a flux with each of the sides of the box, right? And that's the very important part of this step, right? There's a very specific reason. I lost my chalk again. Oh, there it is. There's a very specific reason that we chose a pillbox for a plane, right? With the E field going through the one surface. Because we know that there's going to be something very significant about, we know that the E does not depend on the A, so this will boil down to E dot A is equal to Q, well, I don't do the Q enclosed yet. So it's E dot A, but we know this to be E A cosine theta. Where this theta is the angle between the electric field and the normal vector with the surface, which is good for the top and the bottom, right? Because this is going to have some normal vector that goes directly above and runs perpendicular with the surface. But on the side, it's going to be completely different, right? This is going to be running parallel to the surface, which means it's going to be perpendicular to the E field. So if we were to add up every single contribution of this area, right, they all exist under this A, then we'll end up getting EA from the top, and EA from the bottom, and then from every single side, this cosine is going to be cosine of 90, which is going to be 0. Q enclosed over epsilon naught. There we go. So that's going to be all of the contributions of that's going to be all of the contributions of
Did you say an infinitely
the
long
flux.
charge plane?
Yes, an infinitely long charge plane. Just think really, really big, okay? It doesn't need to be infinite. It could just be really, 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 really big. We're physicists here, okay? What does he call it? Yeah, he calls it infinite plane. Okay. Now, if we want to simplify this, we can simplify it to 2EA is equal to Q enclosed over epsilon naught. Now this one's going to be a little tricky because let's write out the E is going to equal. We're going to do the same process that we've been doing. Q enclosed.
If it was not infinite, you would have an issue close to the edges.
Well, if it's really, 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 really big, we don't need to worry about the edges. We're not going to do fringe stuff. We're not going to do fringe stuff, okay? It's true. It's true. It's very true. I won't argue that what you're saying is true. I'm only going to say it's not relevant. But yeah, if you're actually in an experimental lab and you're working with the fringe charges, then or working with an infinite plate or whatever, or not an infinite plate, but just a finite plate is what I meant, then you will have to worry about the way that the electric field behaves around the edges, because it's not going to be perpendicular to the surface. Well, it's not going to be perpendicular in this sense, but it's all well documented, and there's lots of literature on it if you're interested in it, Tyrion. We got to stick with Griffiths, except when we don't. So now we have the first step done. Like, we've written the electric field in terms of Q enclosed, and but one of the problems is we still have the Q enclosed. Like, we can't solve any of these problems with Q enclosed there, so we got to fix that. And it turns out that we can do the same thing. We can invoke on this. This charge density is going to equal Q enclosed over area, right? Because the area is what's enclosing the charge. And that's what the surface charge density is, right? This is a surface area. So they're going to say that this much surface, I mean, think about it. It's going to be like the surface on the plane is directly attached to the top of the box, right? Pretend that the sides have no dimensions, right? They're just... So the top is going to be directly mappable to the surface, which means it's going to have Q enclosed charge exactly associated with A area. Now, that means that Q enclosed is just going to equal sigma A. We have sigma, that's part of the problem. It was given to us in part of the problem. So then we can rewrite this as Q enclosed is equal to sigma A over 2A epsilon naught. The A's cancel away, and we get sigma 2 epsilon naught. Now, that's an interesting thing that we see here, right? Namely that this sigma charge density and this 2 and this epsilon don't depend at all on distance. Now, this is very specific to the infinite charged plane. If you wanted, like I said, if you had finite charged plane, it's going to be different. But the infinite charged plane, it does not depend on distance away. So even if you have a really, 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 really large plate, charged plate, and you're just this tiny little microscopic thing above the plate, and you're trying to measure the electric field, then the farther you go away from the plate, it doesn't matter. It's going to be the same charge. Or the same electric field, excuse me. And it's weird and not intuitive, but the idea at first is basically think of it like this, right? Think of it as pretend you're in an open field, okay? And the open field is actually a charged plate. Just pretend, okay? Now, and the field is infinitely long, so just pretend you're in a field that's really, really, really big. It's big enough that it doesn't really matter, right? As you start to float away from the field, okay, so you're in a rocket ship, we'll call it, and you're taking off from the field, you're flying away. Then as you look down, the range of what you can see, the things that are interacting with you, via photon in your retina, whatever, is getting larger, right? It's like, what is it? Conical? It's a cone shape. Is that conical? Did I get that right? As you go away, there's more interacting with you. So that's the idea of this infinite charged plane.
You can never escape an infinitely charged plane, my friends tells me.
It's true. The farther you go out, the more you're interacting with, and the effects will be exactly the same, no matter how far away you are. Which is just an interesting thing. But let's talk about something that's more reasonable. What if we have two infinitely charged planes? Oh, so this is the answer to the question, by the way. That's the answer to the question. So now, we did it. We did the first step one. We set up our thing. Step two, we evaluated the electric field for some certain Q enclosed. Step three is we're profiting now. So you're welcome for all of the profit. Now, suppose we have two infinitely large parallel plates with opposite surface charge densities. Okay, and we'll say this one is plus sigma.
Planes is a more reasonable situation.
But we can actually, so we model this as two infinite planes, but the reality is there's something special that happens here that like we use every day in everything. And what do you guys think it is? What do you guys think exists? Not infinite planes. They're not infinite. They're very finite. But the overall phenomenon is relevant because of the size of what we're actually measuring inside here. But what exists is two parallel plates. Man, if that didn't give it away, I'm just not sure. I'm just not sure what could. Two parallel plates with charge. Capacitors, very good, Backman. So capacitors exist as you can have a two parallel plate capacitor. So let's see what's going on with the E field inside. So if we look at the sides of the plates, okay, we can establish that the positive plate is going to have.
Capacitor, what you asking?
I don't even know what to say to that. Okay, we can say that the positive plate. So if this is sigma plus, let's say plus sigma. I don't even know what to go with that, Tyrion. So if this is sigma plus, we can see that the electric field is going to be going radially outward, right? That's by convention that we have the electric field radiating outward from a positive plate. From a minus plate, it's going to have the opposite effect. It's going to be radiating inward. Now, what happens beyond the plates are the E field behaves the same way. So this positive plate is going to continue propagating that way outside of this plate, and this plate is going to have an E field that continues to propagate this way. Okay? So what happens to the E field here is, well, these two are opposite, equal and opposite, so they're going to go away. These two are equal and opposite, so they're going to go away. And here we have an E field with twice the strength, because you have two of the E fields going in the same direction. Like I said, E fields have superposition laws that make it so that we can just add up the E fields that you get here, right? And in turn, that the electric field from a parallel plate capacitor is just going to be E is equal to sigma epsilon naught. Bachmann just took electricity and magnetism, which is not this version, but the one for intro physics, and he knows the prescription method that I used, which was seemingly a lot more exhaustive and was definitely aimed at getting more points on an exam. Not necessarily solving it, but telling the professor what they wanted to hear. But yeah, so that's what happens inside a parallel plate capacitor, and of course electricity can be stored inside that electric field. Now, let's talk about the curl of E. And the curl of E has a very weird thing that, like NC was saying, and I was mentioning as well, is if you wanted to do variational methods or variational calculus of variations, this would be a very relevant spot to do it. So let's go over that and see what. I'm not going to do it. I don't think I have the capacity to do it on the fly. But I do recognize when it shows up. And this is one of the situations where it shows up. Now, let's see here.
I see what you did there.
Okay. The curl of E. Okay. So again, we have another equation, another Maxwell's equation. But this isn't going to be the Maxwell's equation, except under the one guise of it is the Maxwell equation if we're talking about electrostatics. But once we talk about electrodynamics, this Maxwell equation will change. But electrostatics, this is the second Maxwell's equation for electrostatics. The E field. Remember, this is about Maxwell's equations, right? So I'm going to try to reference them back to them as much as I can. 1 over 4 pi epsilon naught. This is just writing down the E field of a source charge on the origin. So now we have a source charge on the origin. So instead of using crazy R's, we're just going to use regular, old, plain, boring R's. We'll have some three-dimensional axis where this is our source charge, Q. And we're going to have two random points in space, okay? So we'll pick A. We'll pick A here and B here, okay? And then we're going to just draw a random path, any path, from A to B. So this is A, this is B. From the radius, there's going to be radii away from the source charge. We'll call the one to A radii A, and the other one radius B, radius A and B. And
I don't like the path you chose.
Don't care. And we're going to find what the electric field is along this path, okay? So we're going to be rigorous about it. We're going to let this be 3 dimensions. It is 3 dimensions, and we're going to use... we're going to use spherical coordinates, because you'll notice we use spherical coordinates a lot, because that's the symmetry that we're dealing with particles, right? Particles have charged particles. The electric field radiates outward spherically, so that's the symmetry that makes a lot of sense with most of these things, especially with particles. So we're going to do an integral from A to B of the electric field along the line that along some random line. Like I drew some random line. You can draw whatever random line you want. Tyrion wants to draw, he wants to draw whatever. So sure, whatever. And then we're going to put the spherical DL. So DL spherically in 3 dimensions is dr r hat plus r d theta theta hat plus r sine theta d phi phi hat. Okay, so that's the whole DL for sphere. So any line and spherical coordinates we can associate with this. And so let's plug it into our integral. So now if we were to write this out, E dot dl, and just evaluate this term before we get back underneath the integral, we could do the cosine of each of these, but notice how r, theta, and phi are all going to be perpendicular to each other. So every time we run into a cosine of r dot, or of r hat and theta hat, or r hat and phi hat, or theta hat and phi hat, then we'll end up having a 0 for the term. So really the only thing that exists in here is where this r and r are dotted together. That's the only thing that shows up. Because this is r hat. So when you start dotting it through all of these, every time it hits theta and phi, it goes to 0. Okay, the whole term goes to 0. And which is another one of the beauty things of using spherical coordinates with electric field. So now, because it'd be super messy if you didn't. It'd be very, very messy if you try to do this in Cartesian. So now this E dot dl becomes a scalar, right? The dot product's a nice, easy scalar. And it's just 1 over 4 pi epsilon naught q r squared dr, because this is a scalar. This is a magnitude as well, so we need to include that. So now we have this term. We can stick it back under the integral. We get the integral from A to B of 1 over 4 pi epsilon naught times q over r squared dr.
Oh, so now you talk beauty. I see how you value my input.
See, that's the type of beauty that he was talking about, the important kind. So now we can evaluate this. Let's evaluate this integral. It's basically we have r squared here and dr on the bottom, so we're just going to do the inverse power law, or the reverse power law, whatever you want to, I don't know what you call it. What do you call it? I don't know what you call it. 4 pi epsilon naught integral of a to b, so minus that integral of a to b, because the minus from the minus 2 comes out front, the 2 goes to 1, and you get, there's no more integral though. Oh, and I used the eraser. Look at how much chalk that leaves behind. I thought erasers were supposed to get rid of chalk, not introduce it. Okay, so then 1 over 4 pi epsilon naught, and then we do the integral, we get the results. Read from the notes, Eric, and we get q over r evaluated at rb over ra. Of course, this is just subtraction, so we can just rearrange these terms so that this is positive and these flip. And what do we get? We get q over 4 pi epsilon naught times 1 over ra minus 1 over rb. Now this is good and all. This is just finding the electric field along a line. It's all good, Chili. Don't worry about it. It's you have to work your way up to this usually. But this is what everybody wanted to see, so this is what we did. But I'm glad you're here, and hopefully you'll learn something about electric fields. We're almost done. We're almost done. We're in the last few steps. So this is what we get. This is a line integral along, whatever line you choose. That's all well and good. But now if the line is closed, okay? So if we want to do, if we define A here and B here, wow. Let's do something different. Let's draw a line first and realize that it's closed. Then the initial one's going to be here, and the final one is also going to be there. That makes more sense. And then therefore, this is going to be what? Well, it's going to be 0. So for a closed line, for closed loop, the line integral of E, so E dot dl, that's what this means, this closed loop, is equal to 0. So that's the notation we use for a closed loop, okay? Which is a very important. It's a very important thing. Why? Well, because we have this thing called Stokes Theorem. Stokes Theorem says that if you have a surface integral of a curl of a vector, so now you're taking some two-dimensional surface, you're taking the curl of some vector that exists in the two-dimensional surface. What happens? Well, it's actually equal to the line integral along some path of that vector dotted with some closed loop. Okay?
Dance monkey dance.
So Stokes' law says this. We can also say that this is true, so this E right here. So that means if this is 0, this whole thing has to be 0, and subsequently the curl has to equal 0. Why does the curl have to equal 0? Because the area can't be 0. It's an area, right? Okay, so now let's talk about this curl. So this curl is basically saying one thing, right? That this is the second Maxwell's equation if you're talking about electrostatics. But let's talk about this curl. This curl is very interesting, right? This saying that this line integral equals 0 is different, and this is where the variational method would come into play if you're really strong with variational method or variational calculus of variations. Is it saying that it doesn't matter what path you take? The path will always, it doesn't matter. So if we draw something like, you know, this, where we have a point A and a point B. Oops, why did I do that? Point A and point B, we could do some dramatic path out here, and then a very short path in that direction. And what this means is it doesn't matter which path you take, A and B will end up with the same result. Hey, Dr. Derp. The curl result shows us something interesting, right? That namely that the electric field cannot be something like this. It cannot change with a variable in a direction other than itself. Why? Well, because the curl is not going to be 0 of that function. The curl is going to have some real thing. So if we're talking strictly electrostatics here, where the charges are not moving, once the charges begin to move, things change. So let's talk about a function v, and we'll unpack what v is in a second. I write it right in my notes like that, but you can hang on to that for a second. E dot dl is going to be the path, and we're just going to pick some random path. So again, go over to here. We'll just pick A and B. We're going to start at some origin point and then go to some radius distance away. So we're going to pick arbitrary points of two things so we can find a potential difference. So if V is the potential, we're going to make some assumptions here and say that V is the potential. We're kind of defining it to be. We want to know how the electric field along that line is going to change. That's, again, very important to what the potential is, as I said earlier. So we can say we're going to pick some arbitrary starting point as this like fancy O, going to the point where we're interested in B, E dot dl. And now we can also subtract. Oh, we're doing a difference. So we're going to actually, if we subtract it, we'll actually have to change the sign. So it's plus from this arbitrary starting point to A. We're following Griffiths for this, by the way. If anybody's interested in following along, we're using Griffiths. I'll just teach there's a point with respect to where there is a body purely rotating. Oh, I see. I'll look at that in just a second, Pop-Tart Moses. Sure. Let's see here. So, if we then, again, we're going to do this thing where we take the boundaries and flip them, and then change the sign. So we get minus, and then these O's are going to, yeah, I don't want to say contract like tensor indices, but they're basically going to go away from the rules of integration, and we'll get A to B, because we're going to be going from A to O, and then from O to B. And then that's going to be E dot dl from A to B. So now, again, we're back to this original thing where we started with, but then we said, hey, if you make this a closed loop, then it's going to be 0, and that's the point, is finding the closed loop being 0, and then using Stokes' law to get to the curl of E being 0, means that it doesn't matter which path you take, this integral is not going to change, which makes this function valid. Okay? That's a very important but subtle thing, is what Griffiths says. So now the fundamental theorem of gradients states that you can take you know, a change in a function evaluated at 2 points, so VA minus VB is just, you know, is basically just going to be some integral of from A to B of the divergence of V evaluated along some line, right? That's just an integral. You take the derivative of what's inside here, so then if you take the integral of the derivative, you just get the function itself. Okay? That's the fundamental theorem of gradients. So now we have this is equal to this right here. This is equal to this, so we can set those two things equal. And what do we get? Well, we get that the integral from A to B of delta V dot dl is equal to the negative integral from E dot dl from A to B again. And what does this mean? Again, another implies that the electric field is actually equal to the divergence of the negative divergence of the gradient, of the potential, excuse me. The gradient. I don't know why I keep calling it divergence. The gradient of V. Okay? So that's the idea. We know that because this integral, this path along from A to B does not matter, then the curl is true, and the curl being true means that, oh, I'm sorry, that was backwards. Because the curl is true, we know that the path from A to B does not matter. It's not important to how it changes. And that means that we can call this some function. We can evaluate that function as the potential, basically how the E field is changing along some line, and then evaluate how the E field is changing along some line into some random point of reference with starting at some, whatever you want, O, and then going to R, and then we can do some manipulation of integrals to find out that the electric field is just equal to the gradient of the V. Okay, we're done. Electricity and magnetism, part 2, completed. Let me get to these good people in chat. Hello, everyone. Hi, Dr. Durr.